a little science thing. I want to just give you an idea of the way things go, and I want to talk just a little bit, and I'm going to talk about some of my own work, because that's what I know best. I want to talk about animals. But if you plot how much energy they need, things scale in an extraordinarily simple way, despite the fact that this is the most complex and diverse system in the universe, probably. And each one of these evolved in its own unique environmental niche. Each one of these is a highly complex system. Each cell is a highly complex system. Yet, in terms of this most complex of phenomena, that is metabolism, somehow they scale in a very simple way. That is, things are going up by factors of 10, the mass is going up by factors of 10, and the metabolic rate is going up by factors of 10, and you can see on this, if I go back to the original slide, by factors of 10, you operate like a light bulb. So each one of us here is like a light bulb. And may I just say the following, that for us in this room, if you ask how much energy do we really use a day to stay alive, meaning not just, you know, we have this building, we have the cars, we have this whole infrastructure, you use about 11,000 watts a day. You are bigger than a blue whale in terms of how much energy you need. And that's why the planet is in such terrible shape. You evolved, each one of us 10,000 years ago, 20 generations ago, used 100 to 200 watts. Now we use 11,000, and we're killing everything. This is the scaling law, meaning mass to the 3/4, meaning if you increase by 4 orders of magnitude, you increase the mass by 10,000. The metabolic rate only increases by a factor of 1,000, so there is an extraordinary economy of scale. Extraordinary economy of scale in life as you get bigger. And there's a graph of it. And I have some numbers there, but I'm going to go through very quickly because I don't have much time. But if you look at any variable you can think of, here's a trivial one, the radius of your aorta, that's the tube that comes out of your heart. It also scales in a very simple way, despite the fact that evolution has been acting on all these things. And so it is with here's your heart rate. Your lifespan increases similarly. That is, the heart rate decreases as mass to the 1/4. So if you increase by 10,000, heart rate goes down by only a factor of 10, 1 order of magnitude. Lifespan increases as mass to the 1/4, and if heart rate decreases as mass to 1/4, you multiply them together, you see that the mass to the 1/4 disappears, and the total number of heartbeats in the lifespan is the same, whether you're a shrew that sits on the palm of my hand, roughly a human being sitting in this room, or a whale that is twice the size of this room. So you have this idea that big things live a long time, pace of life is very slow, and small things, the opposite. Pace of life is very fast, don't live long, and so forth. Pace of life is very fast. And I'm showing you these to show that there's extraordinary regularity underlying the extraordinary complexity. So there's an extraordinary simplicity in the data. This is not theory, this is the data. And underlying this is networks. The reason for this is that there are universal, generic properties of the networks that sustain life, whether it be within a cell, whether it be within a multicellular organism such as us, our circulatory system or respiratory system, or whether it be the virtual network that is part of an ecosystem. Okay? These all have generic properties, and I wrote them down there, you don't have to read them, but they're universal properties. And if you take those properties and you put them into mathematics, all those scaling laws drop out. And so you get a description of, I've skipped over 10 years' work here, but this is the essence of it. You get a description of much of the way life is from intracellular levels all the way up to ecosystems. And these are all highly complex systems, so underlying complexity is often simplicity. So there's a bunch of data. But I hope it gives you a little flavor of the kinds of problems and the kinds of thinking that go into thinking about some of these things and the kinds of scope of problems. That's what I wanted to show you, showing you the portfolio of the Scientific Institute. The kind of portfolio of problems which one can address that can be either highly localized or very big. So I'll finish there. Apologize for taking too long.
Okay. very much, Joe.